right? See, chemical kinetics mainly type factor in the and what is the mechanism that is followed by the reactions. Primary term. Now, the terms like what is rate of reaction, come into more often which we discuss here. So check any change in concentration of the reactant or a product with respect to time is what we call it as rate of reaction, right? So you can see change in concentration of a reactant by time taken. But at the same time, we usually, use stoichiometric coefficient along with it. So the units molarity per second or mole per liter per second. Okay. So why this stoichiometric term is coming? Let me just explain you with a simple example here. Suppose I have initially at time t equal to 0 for this general equation, there is a concentration of A naught and B naught or number of moles. You can assume it like molar number of moles per unit volume here, correct? So we can say that it is A naught and B naught. So then after some time t, you can see this will become A naught minus A times of X. This much is the amount lost. Then this will become B naught minus. Now notice this carefully. For A moles, B moles is required. For AX moles, then we require how much? Sorry, uh, B Bx moles will be utilized, isn't it? Because the ratio, or simply you can write it this way also. Suppose if X amount is lost from here, then what is the amount of B that will be lost here? So for A moles, B moles is been required. So for X moles, Bx by A is required. So therefore, Bx by A is required here, and here it will be Cx by A and dx by A. This is the amount formed, correct? Now, if I write the rate in terms of A, which means how much is the concentration change of A with respect to T. The minus here signifies that there is a decrease in the concentration. That's why the rate, to keep it positive always, you have to introduce this minus. How do I write that? I would write this as, A naught minus X, which is the final concentration, minus A naught, which is the initial concentration of minus divided by delta T. It makes this as X by delta T, correct? That will be X by delta T. Now, if you note, if I write it as minus B by delta T, that will be B naught minus X by A minus B naught of the minus divided by delta T. Correct. Now, in that case, that so that makes B naught to get cancelled. So what do we have here is Bx, by A into delta T. So which is equal to B by A times of X by delta T. Correct. Now, if at all I have to relate this with respect to this, you can notice here minus delta A by delta T is equal to B by A, right? Times of, minus delta B by delta T, isn't it? Sorry, A by B. Okay. So A by B times of this. So if I bring this A to the other side, I will get this as minus uh, 1 by A times of minus delta A by delta T, that is equal to 1 by B times of minus delta B by delta T. Okay. So which means all of these factors can be related with respect to a certain rate, which will be equal. Now, in this case, it will be 1 by C into delta C by delta T, and that will be 1 by D into delta D by delta T. Got it? Yeah. This is how we relate. So this is what we call it as rate of reaction. So rate of reaction will be equal to minus 1 by A by delta T, or minus 1 by B, minus 1 by B, delta B by delta T, or 1 by C, delta C by delta T, or 1 by D, delta D by delta T. This is how rate of reaction can be used. Now, what do we call minus dA by minus delta A by delta T? This is called as average rate of disappearance of A. This is about disappearance of A. Likewise, if we write about the B factor also, it is the same. This is B by T, and that will be disappearance of B. Similarly, I can write it as plus delta C by delta T, which is equal to appearance of rate of appearance of C. Likewise, we can also write that for D also. So if we write this as delta D by T, that is for D here. So you can, everybody notice what I have written. This is what is rate of reaction, and these are the terms that are used to describe the rate in terms of A, in terms of B, in terms of C, and in terms of D. All of you understood that? These are average rate of disappearance of A, B, and appearance of C and D. Okay. So I hope all of you understood how the rate of the reaction is related with all the stoichiometric coefficients, as well as how they are related with respect to rate of the reaction. Okay. Now, this is also called as average rate of the reaction. Average rate of the reaction. Okay. Here, for instance, if you have anything like, you know, I'll write one more example here. If you have 2N2O5, sorry, 2NO2 is becoming N2O4 like this, let's say. And now I have to write the rate of reaction with respect to NO2. Then I will write it as 1 by 2 delta of concentration change of NO2 with respect to delta T. That is what we write it as the rate of the reaction. Got it? Now this is with respect to NO2. If I express the same, I can also write this with respect to N2O4 concentration upon delta T. So this is the rate of reaction. Clear, everyone? So I hope all of you understood how to relate the rate of the reactions in general. Yeah. Now, what is instantaneous rate? See, instantaneous rate is when the limit delta T tends to 0. Correct? So if we write this as minus 1 by delta A by delta T, but here limit delta T tends to 0, which means as it becomes lesser and lesser, this value approaches to a point, and that can be expressed as dA by dt. So dA by dt basically is the slope of the curve at a point. So in case if the concentration of A is decreasing this way, so at this point, how much is the rate change? That is what is the rate of the reaction is what we express as dA by dt. Okay. Now, since we are relating with the rate of the reaction, then I have to write it as minus 1 by A dA by dt. Similarly, minus 1 by B dA by dt plus 1 by C dC by dt and 1 by D dt by dt. So this is what we call it as the instantaneous rate. Okay. Suppose if this is, you can say average rate. Okay. If I use the term average rate, so average rate will be equal to A1 minus A2 divided by, T2 minus T1, right? So that is the final and initial limit. Correct. So this is the average rate, but whole of this I need to multiply with 1 by a with a minus charge. So that will be rate, average rate. Same way, if at all I write instantaneous rate, then that will be equal to minus 1 by a dA by dt. So that's it. This is what you will write. So dA by dt here will be the slope of the curve. Correct. So you can see rate of reaction can be represented as decrease in concentration by time taken. If XA plus YB are giving products, then I can say rate of disappearance of A or rate of disappearance of B. I can write this as minus dA by dt minus dB by dt. While if you write the rate of the reaction, then I will write it as minus 1 by x dA by dt. And the rate of the reaction will always be equal with respect to all the compounds participating in the reaction. So this is how you can write the instantaneous rate of the reaction. Okay. So I hope all of you understood these two terms. What is rate of the reaction, average rate of the reaction, average rate with respect to A, with respect to B, and what is their disappearance and appearance of the products and reactants. Got it? So I hope all of you understood these terms. Clear, beta? Right. Now let's see how we can utilize this in terms of problem solving. See the first one. If rate of formation of ammonia is given, find the rate of disappearance of N2H2 and rate of the reaction, with respect to the given equation. Got it? So in that case, what we will do, we know that you can see this is a balanced equation. So I can write it as minus d of N2 by dt must be equal to 1 by 3 times of d of H2 by dt. That is equal to 1 by 2 times of d of NH3 by dt. Clear? So rate of formation of ammonia is given. Find the rate of disappearance of N2H2 and rate of the reaction. Okay. So rate of formation of ammonia is given, which means what is been given is d of NH3 by dt is given to us, which is 5 into 10 raised to power of 2. So now I need to figure out what is the disappearance of N2, which is minus dN2, which is equal to half of d of NH3 by dt, which is 5 into 10 raised to power of 2, which is 2.5 into 10 raised to power of 2 molarity per second, in case if you're writing this as the disappearance of N2. Similarly, the disappearance of H2, correct, that I have to multiply with 1 by 3. So that must be equal to half of ammonia. So which is 5 into 10 raised to power of 2. So therefore, the disappearance of H2 is minus dH2 by dt, which is equal to 3 by 2 times of 5 into 10 raised to power of 2. Got it? Here, everybody. So therefore, it is 7.5 into 10 raised to power of 2, molarity per second. Correct. So please do check, everybody. This is how you figure out how to find out the rate of the disappearance, from the given case. Right. I hope all of you are following. If there is any doubt, you can immediately stop me. Ayushi, Sukita, everyone, all good?
Yeah, sir.
Right. Samyak, Anna, Rabia,
Yes, sir.
Yes, sir.
good. So please try this question now, everybody. You have to balance that first in the acidic medium, then try to figure out what is the ratio of the rates of change of H plus with respect to MnO4 minus. Quick. Right. More. You may have tried it. Just look into it, everybody. See, from here to here, there are No oxidation state changing from +7 to +2. So 5 electrons got transferred. And from here to here, you'll see only 1 electron is transferred. So from +2 to +3, 1 electron got transferred. So if I cross multiply that, I will get it as MnO4 minus plus 5Fe plus 2. That is giving as Mn2 plus 5Fe plus 3. Now we need to balance the number of oxygens, which makes there are 4 oxygens, which results to make it as 4H2O on the right hand side and 8H2O on the right hand, sorry, 8H plus on the left hand side. Thus, that gives you a balanced, overall balanced equation, which is equal to MnO4 minus plus 5Fe plus 2 plus 8H plus. That is going to give us Mn2 plus 5Fe3 plus 4H2O plus 4H2. Got it? So from here, I can write it as minus d of MnO4 minus by dt. That is equal to minus 1 by 8 of dH plus by dt. Correct? So you know that rate R1 is equal to 1 by 8 times of R2. So the question asked is what is R2 by R1? So R2 by R1 is 8. Okay. So R2 is the rate of disappearance of H plus and R1 is the rate of disappearance of MnO4 minus. Correct? Clear everyone? Right. Check it out. What are the factors that affect the rate of reaction? The first is concentration of the reactants of the concentration of the reactants, whether it is solutions or gases, anything. Then temperature. Catalyst will also influence the rate. Partial pressure of the gas reactants. If there is partial pressure given, then that will be influential. Surface area of the solid surface, that will also be influencing the rate of the reaction. Intensity of light, especially in photochemical reactions. For example, two, uh, if you have chlorine gas in light to get Cl dot, then Cl dot reacting with something like CH4, and if it is becoming CH3 dot plus HCl and CH3 dot plus Cl2 again becoming CH3Cl, sorry, CH3Cl plus Cl dot. Now, suppose if this is the rate determining step, that is the slowest step, correct? So, if the overall reaction is concerned, that means you might expect that the reaction like CH4 plus Cl2 becomes CH3Cl plus HCl. This is the overall reaction. But this overall reaction will be having a very less amount of rate as compared to that of light given. The minute if the light is being given, the rate will be increasing very drastically here. Got it? So that's why intensity of light, if it is increased, more and more radicals will form, more is the amount of product formation. Clear? So these factors are directly asked in exams. So please do remember all 6 factors, 1, 2, 3, 4, 5, 6, all of these factors which affect the rate of reaction. Now, the next important aspect about rate is understanding how to write the rate of a reaction in terms of various formulas. And this can be done by using something called rate law. According to rate law, if you're operating a reaction at a constant temperature, let's say this is a generic reaction, then rate can be expressed in terms of concentration of the reactant raised to their coefficient powers. Okay. So raised to the power of some numbers here. Correct. So if I write it as in mathematical equation, it is rate is equal to some constant into a raised to power of x and b raised to power of y. This way of expressing is called as differential rate law expression. And now notice if k the constant which is there with respect to rate, that is called as rate constant. X is called as the order of the reaction with respect to A. Y is called as the order of the reaction with respect to B. The sum of X plus Y is what we call it as the order of the reaction. Okay. So order basically is the sum of the powers of reactants in the rate law expression. Now listen, order may be integer value, it could be fractional value, correct? It could be plus, it could be minus, any of that could be possible for order. And order is something which is only experimentally derived. So empirical values are taken at various at different times. Based on that, we calculate what is the order. Then rate constant depends on temperature and catalyst only. Okay, here depends on temperature and catalyst only. Clear? Now notice. Generally, whenever we say chemical reaction is happening, if you want to explain the kinetics, the easier way to explain is that assume that when the particles are uh, about to make a product, that means they are colliding with each other. That means they are trying to bombard with each other so that their bonds are broken. So suppose if at all I have a reactant has some number of bonds, and now to convert into products, it has to break some bonds initially and then make some bonds. So when a reactant breaks his bonds, its potential energy increases because you are pushing a lot of energy into that molecule to break that bond. So a lot of energy has gone into that species. Hence, the energy of the reactants increases and reach to a maxima value. And thereafter, once it reaches to a maxima where the bond breaking is completed, now the bond making will start. Now the rearrangement of atoms will happen, and after that rearrangement, new molecules are forming, which is by bond making. Now, when the bond making happens, again the energy is released, and the energy of the products comes down. Correct. So, in a way, I can say if I measure the reaction or rate of progress with respect to time versus the potential energy change then that potential energy with respect to rate of progress, you notice that reactant energy will increase first, thereafter it decreases. Okay. The highest energy state where the reactants are reaching, that is what we call it as transition state. That is what we call it as transition state. Clear? And the energy that is required for reactants to reach there. See, reactants already have some energy. And on top of that, this much extra amount of energy that is required for them to reach to this transition energy. So this extra minimum amount of energy that is required is what we call it as activation energy. Okay. So you can see transition state TS, right? It is the state of the reactants when they have achieved maximum energy. Activation energy is the minimum energy required by reactants to convert them into products. Got it? Now, notice this one carefully. If a reactant is becoming a product just via transition state, then such a type of reactions are called as elementary reaction or also known as single step reactions. Single step reactions. Got it? Some of you must have done reaction mechanism in which, you know, you might have learned about SN2 type of reaction, E2 type of reactions, EI type of reactions. These are all single step reactions. That means they happen in one step. Got it? Whenever there is only one step, which means we are going from reactant directly to product, but just via transition state. Okay? So we are just going through the transition state. Now notice There is one more type of reaction known as complex reactions or multi-step reactions. Complex reactions are multi-step reactions. It is like from A to products to form, we are going through something called intermediates. Like in organic chemistry, we have carbocation, carbanion, radical, benzene. These are all intermediates which we noticed. The same thing here. So B and C are intermediates. Okay. Now, from A to B, if it has to go, probably as the bond breaking happens, directly it is not giving products. First, some bonds are being made, and thereafter, few more bonds have been made, and finally, all the bonds have been made. So when some bonds are still yet to be prepared or yet to be made, that means it still have some charge on it, then those are called intermediates. So here B and C are intermediates. And whenever there are intermediates present between reactants and products, you will have multiple transition state. And in short, you can see number of intermediates present will always be equal to, right? Number of intermediates present will always be equal to number of transition states minus one. Got it? So you can see there are three transition states we are getting. Now, every time there is an transition state, that means there is an activation energy associated with it. So this TS1 will have an activation energy E1. This has activation energy E2. This has activation energy E3. Suppose if I give you like this, that E1 is greater than E2 is greater than E3, correct? That implies step A to B is the slowest step, slowest step in the overall reaction, in the overall reaction. Okay. And remember, the slowest step in the overall reaction is what we call it as rate determining step. Determining step, which we call it as RDS. Okay. So in this case, for instance, E1 looks to be higher value. Hence, we can say A to B is the slowest step. So here I can write it as RDS or slow step of the reaction. Okay. Hmm. Yeah. Right. Now notice everybody, when you write the rate of reaction for any reaction, A to B is giving product. Okay. Now notice this. I told you that according to the rate law, we can write it as K into A raised to power of X and B raised to power of Y. Suppose if you notice the stoichiometric coefficients here, it is A and B. If the X value matches and Y value matches, correct? That means the reaction can be elementary. It can be, I said. That means it may be complex also, but it is elementary. Okay. But if I said the reverse way, that if there is an elementary reaction given, then A has to be equal to X and B has to be equal to Y. Got it? But if it is a complex reaction, that means X may be or may not be equal to A. Got it? But if in the case of elementary, we can definitely say the stoichiometric coefficient on the order of the coefficients, order of the reactants will be always same. Clear? Take the okay. Then notice this question, everybody. This was a JE question which was asked. 2NO plus Cl2 is giving 2NOCl. Rate is given like this. Okay. Now rate is given as 2 and 1, which is confirming that it could be a complex also or an elementary reaction also. We cannot say it is definitely elementary. We cannot say it is definitely complex, but we can say the chances are high that this rate may be elementary, this rate may be complex, but we cannot say that it must be elementary or it must be complex. Got it? Please go through it. If anybody has a doubt in understanding what is elementary and complex reaction, do ask me right away. known as molecularity. Let us learn molecularity. See, molecularity is more of a theoretical concept, right? And it is only defined for elementary reaction. That is, total number of reacting molecules which are participating in an elementary reaction to form the products is called as elementary reaction. Sorry, is called as the molecularity. That is, if A plus B is giving C plus D, considering that it is elementary reaction, then molecularity of the reaction is A plus B. That is this A plus B. Correct? If you may recall that we have come across reactions like E1, E2, then we will be learning about SN1, SN2 like this. This numbers 1 or 2 are molecularities. These are all molecularities. Got it? That is, we call this E1 reaction as unimolecular reaction. Unimolecular reaction. Similarly, SN2 is called as bimolecular reaction. Got it? That means during the slow step, there is only one molecule involved if it is E1. Similarly, if it is SN2, that means there are two molecules involved in the slow step of the reaction or rate determining step of the reaction. Clear? So you can see, suppose if you have 2A plus B giving C, then I can say the molecularity is 3, correct? But if at all I have A plus half of B giving half of C as a reaction, I can't say that the molecularity is 1 plus 2. This would be incorrect. Yeah. Because molecularity is always a positive integer value, which means first I need to convert this equation back into this kind. Got it? Hence, this way of writing and expressing the molecularity is 1.5 is incorrect. Instead, you write all the reactants and products, sorry, all the reactants in the form of, simple integer values and then take the sum of all the reactants. That becomes molecularity. Now, here is a catch. Just because a reaction is given 2A plus 4B giving products, it does not mean the molecularity can be 6. Okay. Reason being, molecularity is only expressed for a elementary reaction. Got it? So for an elementary reaction, right? If at all I have to make a product, then I'm expecting there should not be any intermediates. That means all the bonds in A, all the bonds in B, which are breaking and then making, they all should happen simultaneously to get the product. Got it? Now tell me, what are the chances that 2A molecules, 4B molecules, all of them are colliding with each other simultaneously? Okay, it is like this. I'm saying there is a molecule A, there is a molecule A, and then I'm expecting one molecule B from one direction, this from one direction, this from one direction, this B from here, this B from here, and this B from here. Correct? You can see 2 is to, sorry, 4 ratio here, like this. This, this collision, this collision, probably this collision, this collision, this collision, this collision, and this collision, even this collision, correct? We don't know. All of these type of collisions which are happening, what are the chances that all these particles are colliding with each other in the right orientation simultaneously? Okay. Because if you do not break them simultaneously, correct, then you may not get the product. So chances of these many particles, trying to collide with each other simultaneously is impossible. You know how much maximum number of collisions that can happen simultaneously, correct? Maximum we can say two collisions. That means one particle of A, correct, and two particles of B, this collision. This is still high. I mean, this is sufficiently probable. I mean, we can say probability is high in this case. That is, then how many particles are involved in it? B is involved, A is involved, B is involved. So total 3 molecules are involved. So that's the reason molecularity in reality can never cross 3. Got it? That's why if you have been given anywhere like 2A plus 4B giving product, then without any doubt you can say that this reaction has to be a complex reaction, because just in one step we cannot get a product. Understood? Moreover, this reaction has to happen, it has to definitely go through multiple steps. Now you can see every step that happens in complex reaction is also an elementary reaction. Like 2A plus B giving A to B, that is one elementary reaction. A to B plus 2B giving this product is also one elementary reaction. And this A to B3 reacting with B giving product is also another elementary reaction. So basically, this complex reaction is a summation of three elementary reactions. Now, within these three elementary reactions, let's say this is a rate determining step, which is the slowest step of the reaction, slowest step of the overall reaction. In that case, for this particular complex reaction, we can say the molecularity is 3, because molecularity is only judged on the basis of rate determining step. So I can say in the rate determining step, there are 1 plus 2 molecules involved. So we can say the molecularity in this reaction is 3. All good? Okay. Generally, if the statement is given, then it is true statement. Okay. Right. That is, overall molecularity of a complex reaction is not defined. It is not like we can take the average of the molecularities or something like this. No, there is no overall molecularity, but molecularity of a complex reaction can be said, okay, it is 1 or 2 or 3, but these numbers 1, 2, or 3 are on the basis of the slowest step. Everybody understood? So by theoretical definition, as a statement, I can say molecularity is defined only for elementary reaction. True. Overall molecularity of the complex reaction is not defined. True. Okay. Molecularity of a complex reaction, molecularity of a complex reaction is 3. Is it correct? Or is observed between 1 to 3? Answer is yes. Because we are not talking overall molecularity. We are talking about molecularity in the slowest step. Okay. Now, quickly, let's assess the differences. Molecularity is a positive value. Order is a fractional or integer value. Molecularity is more theoretical. Order is experimental. Molecularity is defined for elementary. It is defined for both elementary and complex. The maximum value is 3 here. Maximum value has no upper limit. Okay. Now, let's notice this question, how it is been framed. For an elementary reaction, 2A plus B2 is giving 2AB. Calculate how much the rate of reaction change if volume reduces by 1/3 of its original. Okay. Now the question here is, I mean, what we need to understand is that this is elementary reaction. So for an elementary reaction, rate can be very easily written that rate of the reaction R is equal to some constant into A raised to power of 2 and B2 raised to power of 1. So I can say here the order and molecularity are same for an elementary reaction, and in this case it is 3. Okay. And therefore, if you notice, this rate is proportional to K into number of moles of A by volume power 2 into number of moles of B2 by volume power 1, which implies rate is inversely proportional to V cube. Correct? Which means if I write it as R1 by R2, we can say it is V2 by V1 raised to power of 3. Correct? So I need to check out how much amount of rate changes. That means I need to figure out R2. So R2 is equal to R1 times of V1 by V2 whole cube. So you can see R1 into V1 by volume was reduced to 1/3 of the initial volume. So that overall raised to power of 3. So that means it is 27 raised to power of R1. So R2 will be 27 times more than that of R1. Everybody clear on this point? Please check. I hope that is clear, everybody. See the next question now. If it is been given that N2O5 is decomposing by a first order kinetics, or let's say it is a first order kinetics, and it is given that minus d of N2O5 by dt is equal to K1 into N2O5 power 1. That means it is first order. With respect to NO2, K2 into power 1. With respect to O2 also, it is K3 into power 1. In that case, how do we relate K1, K2, K3? Now, you know that how the disappearance and appearances are related with each other. That is with respect to rate of reaction. Rate of reaction can be written as d by dt of concentration of N2O5, which is equal to, sorry, minus of 1 by 2 of 1 by 2 of d of NO2 divided by dt, which is equal to 1 by 2 of d of O2 by dt. Correct? So now you can see minus d by dt of N2O5, correct? That is given as K1, here K1 into N2O5, while d of N2O5 by dt, half of it is equal to K2, correct? So I can write this as 2 times of K2 because this entire thing is given as K2 into T. So I can write this as half of this entire thing, you know, half of this entire thing here will be equal to K2 into N2O5 by 2, right? And similarly, 2 times of d of O2 by dt will be equal to 2 times of K3 into N2O5. And you know that these three are equal values. So if I equate them, I will get this as K1 is equal to K2 by 2 is equal to 2K3, which implies 2K1 is equal to K2 is equal to 4K3. Got it? This is what you would have. Clear? So I hope all of you are able to relate that. Right. Now let's talk about the next important term, that is about writing the rate law expression using rate law. We are trying to write the rate law expression for various orders, right? Starting with zero order, then first order, then second order, then nth order, and so on. First, let's see. Imagine there is some reactant, only single reactant giving some product. Okay. And imagine the initial concentration is A. I'll write the concentration as A naught. Okay. And after some time T, there is some X amount of the concentration lost. So that means A minus X will be the new concentration, which we write it as AT. X is defined as extent of reaction. That means how much amount of time it will take for reaction to complete. Okay. Now, in such cases, we can always write something called degree of completion. Degree of completion means how much amount of, consumed amount with respect to the initial amount is present. So consumed amount is X, initial amount is A. So X by A is the alpha value. And alpha value will be between 0 to 1 always. And the percentage completion is always represented as alpha into 100. Okay. If it is 50% completed, we will say it is 50 into alpha. Okay. So this way we can represent it. Clear? So what I'm trying to say is, suppose if you have different alpha values, okay. So if alpha value is half, then we say the time taken, we write it as T50, correct? Or another way of writing is T1 by 2.
So if alpha value is, let's say, 3 by 4, then we write it as T 3 by 4. Acha, T 3 by 4 is nothing but T 75 in terms of percentage, because 3 by 4 into 100 will give you 75 percentage. Got it? Like that, if you have alpha is equal to n by 2, correct? Any n by 2 is given. So then this will be T n by 2. Okay. So this much is the new, time here. So it is an unknown time. It could be anything. It could be half life, or it could be, multiple half lives. Could be anything. So for any n value, you can write it down. Here, suppose if at all I have alpha is equal to n by 2 and a naught initially is a, then what will be at? At will be equal to a minus a alpha. So a minus a into n by 2. So that will be equal to a into 2 minus n by 2. So this will be the value of 80. This will be the value of 80. So keep that in mind for different value of n, how to figure out 80. Okay. Now, same thing I have written it here. So T half, if you have T alpha, you have, how do we write that? 2 by 3 means how much it is? How much is left over? This is the A value. This is the leftover value. Okay. Now listen, applying this to, zero order kinetics. How do we apply this to zero order kinetics? See, if A is giving products according to rate law, I can write that rate is equal to some constant into A raised to power of 0 for zero order kinetics. For zero order kinetics. Got it? So minus dA by dt is equal to K into A raised to power of AT raised to power of 0. AT means concentration at time t. Now, since the any concentration power 0 is 0, so I can write minus dA by dt is equal to some constant. So that can be written as dA is equal to minus K into dt. So if I integrate that dA, initially it started from A naught to go all the way to AT. That is equal to minus K into integral 0 to t dt, which makes it AT minus A naught is equal to minus KT, which can be written as AT is equal to A naught minus KT. So this is the expression for zero order kinetics. For zero order kinetics, you can express the concentration at time t in terms of initial and time taken. Clear? Now, we know that when we write rate, if AT is given, so AT will be equal to A naught minus some X amount lost, isn't it? So if that is the case, we can say that uh, uh, X in this case here, you can see AT is A naught minus X, which is equal to A naught minus KT, which implies X is equal to KT. Another way of expressing that is in terms of uh, X is in terms of how much amount of extent of the reaction happened. Right? If I put them graphically also, how does they appear? Correct. So you can see AT versus T. That will start decreasing this way, because you can see it is Y is equal to mx plus C and slope is negative. Okay. So for this case, I can say tan theta is equal to minus K, and this value is at A naught. Likewise, if I write this as, you know, rate rate with respect to t, okay, then rate is constant because rate is equal to simply k into a raised to power of 0, correct? So this value here is simply k value. That's it. This is the value of k. Done. So I hope all of you understood that how to use this uh, rate law. Okay. Now, as I said, if you want to calculate T50, T75, T100, what is the way to write down? Check out. For zero order kinetics, we just learned that AT is equal to A naught minus KT. So if we are talking about T50, right, that means alpha should be equal to half. Okay, X should be equal to A naught by 2, and T50 should be equal to A naught by 2K. Because if I put AT as A naught by 2, then if I bring this KT on the left hand side, I will get T50 is equal to A naught by 2K. Okay, here. So this becomes the half-life of the zero order reaction. This is the half-life of the zero order reaction. Okay. Next is, if you compare T75 means alpha is 3 by 4. If it is 3 by 4, then AT will be equal to 1 by 4 times of A naught. So now if I put this as 1 by 4, in that case, T75 will be equal to, just go through it here. AT is 1 by 4 of A naught, that is equal to A naught minus K75. So therefore, K75 will be equal to, you know, 3 A naught by 4, isn't it? So have you noticed that if the alpha is 3 by 4, that is the factor I'm multiplying. Therefore, if you have alpha is equal to 1 by n, okay, here, if it is 1 by n, in that case, T of, uh, 1 by n will be equal to, 1 by n times of A naught. That will be 1 by n times of A naught. A naught by K, sorry. A naught by K. Here, similarly, if alpha is equal to, let's say, n by 2, so in that case, this will be, uh, implies T of n by 2 will be equal to n A naught by K. That will be n A naught by K. So please do check, depending upon whatever the value we require, we can accordingly get the alpha values and time factors. Clear? So I gave you this graphically already. How does they look like? Done. Now there is one thing we learned, that here zero order reactions, note that zero order reactions comes to completion after certain time. So because you can see the concentration, initial concentration from A naught will definitely touch at a reasonable amount of time and become zero. After that, the kinetics will stop. Correct? These are the examples you see wherever you use photolysis or metal catalyst as the metal catalyst is utilized for the uh, increasing rate of reaction, like molybdenum, in this case platinum, or hydrogenation. For example, if you take any hydrogenation reaction in the presence of nickel, and so like this. Suppose I have cyclohexene reacting with H2 in the presence of nickel, right? So to get this as cyclohexane. So all these kind of reactions where metal catalyst is involved or light is involved, usually they were zero order kinetics. They all are zero order kinetics. Okay. Now, let's understand what is first order kinetics. Okay. First order kinetics, if you have some reactant going towards product T, then let's say at time T equal to 0, initially, let's say it has concentration A naught, and after some time T, the concentration is AT. AT can be A naught minus some X. X is the extent of reaction. Got it? So in that case, I can say that minus dAT by dt, which is the instantaneous rate, can be written as k into at power 1. Why power 1? Because now we are talking about the first order kinetics. So therefore, I can say d of at by at is equal to minus k into dt. So if I integrate this dA, I'm just writing d by at. I'm writing this simply a. dA by a starting from a naught to at, that is equal to minus k integral of 0 to t dt. Then 1 by x dx. If you have 1 by x dx, the integral value will be ln a. Okay, ln x. So ln a starting from a naught to at, that is equal to minus kt. Okay, so from here I can write this as ln at minus ln a naught is equal to minus kt, or ln a naught minus ln at, that is equal to kt. In simple terms, ln a naught by at is equal to at. Correct? Right. If at all I take this log into ln into log value, I can write k is equal to 2.303 by t into log of a naught by at. Now this is the most sorted formula that we'll be using for first order kinetics. That is how to express the k in terms of a naught and t. Here, now if at all I have to write in terms of a naught, you can see I take anti-log on both sides, so I will get this as a naught is equal to at into kt. Correct? Sorry, e raised to power of kt. E raised to power of kt. That implies at is equal to a naught e raised to power of minus kt. This is another important way of expressing the uh, first order kinetics. Along with that, another way we can express is log of a naught minus log of at is equal to 1 by 2.303 times of kt. Now, if I write this in terms of an equation of a straight line, log of at is equal to, you know, minus 1.203 into kt plus log of a naught. So this would look more like y is equal to mx plus c with a negative slope, right? So we can understand how the graph would be for this case. Along with that, we also know that at is equal to a naught minus x. So therefore, x is equal to a naught minus at. Okay, and you see, if it comes to a naught here, sorry, if it comes to x is equal to a naught minus at, so I can say a naught minus at can be written as a naught into e raised to power of minus kt. A naught I can take common, so 1 minus e raised to power of minus kt. That can be expressed as the extent of the reaction x, which is equal to a naught into 1 minus e raised to power of minus kt. Got it? So this is another important expression that we will be using. So please check all the important ways of writing the integrated rate equations. I have written it. This is about the first order kinetics, everybody. So these are the first order kinetic graphs. First order kinetics graphs. Okay. So here you can see rate versus rate can be expressed as k into at, and at can be expressed as a naught e raised to power of minus kt. So that's why this is also an exponentially decreasing graph. So you can see rate will be exponentially decreasing here. Okay. Now, since this reaction will never come to a completion because it will keep on going, asymptotically, it will keep on going with respect to time. Now, what is half-life? Just like how we defined the half-life in the case of zero order, here T50 is when we have AT becoming A naught by 2. Okay. So in such case, I know that K is equal to 1 by T ln A naught by AT. Correct. So if I substitute that value here, so you can write it as T50 is equal to 1 by K into ln A naught by A naught by 2. So which makes it ln 2 by K. ln 2 can be written as 2.303 log of 2 by K, which comes approximately 0.693 by K. Got it? So half-life of the reaction can be written like this, that is T50 is equal to 0.693 by K. Okay. So you notice one thing, T50 is independent, independent of initial concentration of reactant. Got it? So that's the important part here, that half-life is independent of initial concentration. Now notice, generally, if there is any case given, just by seeing the value of their concentration, we can know what type of kinetics it is. Suppose initially I have 10 molar concentration. Now it has becoming 5 molar concentration. Imagine the time taken is 5 minutes. And from 5 molar to get to 2.5, again, if it is taking 5 minutes, from 2.5 to 1.25, again, if it is taking 5 minutes, in such case, this has to be a first order kinetics because T50 is independent of initial concentration. Whether it is 10 to 5, whether it is 5 to 2.5, or whether it is 2.5 to 1.5, the time taken is same. But check out case 2, from 10 to 5, if it is 5 minutes taken, from 5 to 2.5, 2.5 minutes is taken, and thereafter it is becoming 1.25 minutes, which means it has to be a zero order kinetics. Because for zero order kinetics, it depends on the initial concentration. If the initial concentration becomes half of the given quantity, then the time taken for it to become half life will also decrease it by half. Correct? So second case is a zero order, first case is a first order reaction. Here, usually all the decomposition reactions, notice it here, N2O5 decomposition or peroxide decomposition also, peroxide converting into H2O plus half O2. This is peroxide decomposition. Any kind of gas decompositions or any liquid like H2O2 decomposition, right? Here also gas decomposition, or you can remember SN1 type of reactions, correct? Sorry, E1 type of reactions, right? Or we can see hydrolysis. Generally, hydrolysis reactions are also first order kinetics. So ester plus H2O is giving two acids. Sucrose plus H2O is giving these glucose and fructose. These are all the examples of first order kinetics. Last two are little exceptions because they are not precisely first order. They are called pseudo first order kinetics. Okay. Clear? Now, another important fact you can see is that from A to A by 2, right? If you are taking T50, that is one half-life is been taken. A by 2 to A by 4, two half-lives will be taken. And A by 4 to A by 8, three half-lives will be taken. But have you noticed the denominator? The denominator earlier was 2, now it is 4, 8, 16. It is like a GP. So it is 2 raised to power of 2, 2 raised to power of 3, 2 raised to power of 4, and so on. So that means if it becomes A by 2 raised to power of n, that means there must be n half-lives consumed. So the amount of substance present after n half-lives will be equal to A by 2 raised to power of n. Clear, everybody? So this is another important thing which we can directly express, and we should be able to tell that how much number of half-lives we have taken to reach here. Okay. So I hope the examples on the idea of relating half-lives is clear. Next. Check out, in the case of first order, how do we calculate 75%, 90, 99, and 99.9%? See, first, if it is 75, that means alpha is 3 by 4. If alpha is 3 by 4, AT, which is equal to A naught minus 3 by 4 of A naught, that is equal to 1 by 4 of A naught. Now we know that T75 will be equal to 1 by K ln AT by, sorry, A naught by AT, which is equal to 1 by K ln A naught by 1 by 4 times of A naught. That is equal to T75 is equal to ln 4 by K, which is equal to 2 ln 2 by K, and ln 2 by K is T50. So 75% is gone, means two half-lives have completed. Okay. Next 90%. If you check out 90%, that means alpha is basically, 9 by 10 done. So if that is the case, AT will be equal to A naught minus 9 by 10 times of A naught, which is equal to 1 by 10 times of A naught. So put that value here. So T90 will be equal to 1 by K ln A naught by A naught by 10. That is equal to ln 10 by K. Correct? ln 10 by K can also be written as 2.303 by K. Correct? This is 2.303 by K. Okay. T. In this case, we can also write this as T50 divided by log of 2, because K is equal to, log 2 by T50, right? Into 2.303, right? Sorry, ln 2. So 2.303 will get cancelled. So log of 2. So if I put this as log of 2, that means it is T50 divided by approximately 0.3. So that comes to be 3.33 times of T50. So 3.33 times have been times of half-lives have been consumed at T equal to 90. Got it? Next. If T99 percentage is given, T99 means alpha is 99 by 100. Okay. So AT will be equal to 1 by 100, right? So in that case, K will be, in that case, T99 will be equal to 1 by K into ln A naught by, right? Sorry, into A naught by 100. So that makes it ln 100 by K, which is equal to 2 ln 2 ln 10 by K, or that is equal to, have you noticed something? Ln by K is nothing but 90. Therefore, it is 2 times of T90, and that is equal to 2 times of 3.33 times of T50, which is 6.66 times of T50. This is the value you will get for 99%, if 99% has been completed. Next one, if it is 99.9% is completed, then alpha will be equal to, 99.9 divided by 100. So which means AT will be equal to 1 by 1000 times of A naught. So T 99.9% will be equal to 1 by K ln A naught by 10 raised to power of, sorry, 10 raised to power of minus 3 times of A naught, which is equal to ln 1000 by K, which is equal to 3 ln 2 by K. So that is 3 times of T90, which is equal to 3 times of 3.33 times of T50, which is approximately 10 times of T50. So after 10 half-lives, everybody, after 10 half-lives, we will reach to 99.9% of the compound completion. Okay, 99.9% of the completion has been done. Okay, clear? Next, T 99.9%, which means, alpha is 99.99 by, 100. So that makes K is equal to 1 by 10,000 times of A naught. So T 99.99 will be equal to 1 by K into log of, 10,000. Yeah, sorry, ln of into ln of 10,000, which is equal to 4 ln 4 ln 10 by k, which is equal to 4 times of T50 or 4 into 3.33 times of T50, okay, which is approximately 13.32 times of T50. 99.99 percentage completion means this much amount, correct? So be aware to relate how these timestamps are related with respect to T50. Next, last one is about average life. Average life, to define it as average life, that means basically we are taking something from zero to infinity from all the way, correct? How much amount of change that we are getting, correct? So that after calculation, after doing all the integration, it will come out to be T average is equal to 1 by K. You can directly remember it like formula. You don't have to go through derivation of it. So T average is 1 by K. So if that is 1 by K, you know that T50 is actually equal to ln2 by K, correct? Which is equal to ln2 times of T average. And ln2 is 0.7 times of T average, correct? So therefore, average life is equal to, average life is equal to 1.44 times of T50. Another important formula. The average life of any first order kinetics is 1.44 times of T50. Hey, I hope all of you understood. Please go through it once quickly. Check out if there is any half-life or any other timestamp is bothering. Please check. The next part is about applications of first order kinetics. Quickly check out. First case is about how to write the gas phase reactions. Usually gas phase reactions, you will be given the data in terms of partial pressures. Now you have to write the first order kinetics in terms of partial pressures. Okay. As per in this question, what has been given, if the initial pressure is P naught and after a certain time the total pressure is PT, now we have to express the gas rate law in terms of this P naught and PT. We have to express that in terms of P naught and PT. Now notice this one. If t equal to 0, that is a time t equal to 0, if this is P naught and there is no B and C form, and after some time t, this has become P naught minus some P. Some P is the pressure lost. Then there will be P built up here, P built up here. So the total pressure now will be equal to P naught plus P. Now similarly, when time t equal to 0, if I write in terms of concentration, if this is A naught, and after time t, this will become A naught minus X, X and X. And if remember, if A is something which is following first order kinetics for this reaction, then as per according to rate law expression, I can write rate R is equal to some constant into A raised to power of 1, isn't it? In this case, using this entire thing, we could calculate that K is equal to 2.303 by T log of A naught by A naught minus X. This is what we just learned, because A naught minus X is the amount after time T, correct? Now, I need to somehow replace these terms in terms of pressure, which is P naught and PT. How do I do that? Initial concentration, right? Because pressure is directly proportional to concentration, or it is directly proportional to moles. Okay. Yeah. So in that case, we can say pressure is directly proportional to concentration. So initial pressure, if you notice, this is P naught is proportional to A naught. And similarly, P naught minus P is proportional to A naught minus X. Correct? These are the partial pressure, because partial pressure will be proportional to its concentration term. So if I write this as A naught by A naught minus X, I can also replace that as P naught by P naught minus P. Now I don't need this P term, but I need to replace that P term in terms of P naught term. For that, we can use this. We know that P is equal to, we know that P PT is equal to, P is equal to PT minus P naught. So that implies K is equal to 2.303 by T log of P naught by P naught minus PT plus P naught. My code, get it class. So that will be equal to 2.303 by T log of P naught by, sorry, this is PT minus P naught, sorry, PT minus P naught. So that makes it 2 P naught minus PT, makes it 2 P naught minus PT. That will be the value of K. So K is equal to 2.303 by T log of P naught by 2 PT minus PT, right? So this is the expression we are looking for. So I hope all of you got that. Please check quickly. Let's check case 2 here. In case 2, what we are trying to do is if A is giving 2B plus C, stoichiometrically, the values are different here. That's all. Rest all is the same. And the same thing I have to do, I have to express that in terms of P naught and PT. So let's write that. So this will be initially P naught, right? So now this will become P naught minus P, 2P and P. So the total pressure will be equal to P naught plus 2P. So P will be equal to PT minus P naught by 2. Okay, correct. And we know that we can write this as A naught and A naught minus X, 2X and X. This is at time T. If this is a first order kinetics, I can write K is equal to 2.303 by T log of A naught by A naught minus X. And you know that A naught can be related directly to P naught and A naught minus X can be directly related to P naught minus P. Okay. Hence, this implies A naught by A naught minus X is equal to P naught by P naught minus P. So let me put that value back here. So K is equal to 2.303 by T log of P naught divided by P naught minus P. As a P, we just defined it as PT minus P naught by 2. So that is PT minus P naught by 2. So that makes it 2.303 by T log of this 2 will go into the numerator divided by 3 P naught minus PT. So this is the final expression. So K is equal to 2.303 by T log of 2 P naught upon P naught minus PT. So this is the final expression. Okay, such type of questions, if it is been asked, where pressure terms are given and you need to express the first law, first order kinetics, then you can use this. So I hope the second case is clear, everybody. Right? Good. Now let's see the third case. Okay. I'll come back to those questions. First, let me do the third case here. Right. See. This is the third case where we have case 3, where we have A is giving B and C, but this time I have to express the rate law in terms of total pressure after time T and, you know, total pressure after some time T and then P infinity. Infinity means after uh, after the completion of the reactant, right? After the completion of the reactant, how much is the pressure which is present? So you can see if time t equal to 0 and initial pressure is P naught, correct? And at time t equal to t, this has become P naught minus P, P and P. At time t equal to infinity, then this will not be present anymore. This will become P naught and P naught. So now notice this one. P total is sum of these three, which is P naught plus P, and P infinity is equal to 2 P naught. This is P infinity. Now listen up. You know that A naught by A naught minus X ratio is what we are looking into for solving first order kinetics, which means this is P naught by P naught minus P. And you see, P naught can be expressed in terms of P infinity, right? In terms of this way, that is P naught is equal to P infinity by 2. Similarly, P can be expressed as, Pt minus P naught, and Pt minus P naught can be expressed as P infinity by 2. So these are the terms that we need to add there. So check it out. P naught is P infinity by 2, that divided by P naught, P naught, P naught, which can be written as P infinity by 2 minus P. P is how much? Pt minus of minus will become plus. So P infinity by 2. That's it. So the 2 will get cancelled. We'll get P infinity by 2P infinity plus 2 plus 2 times of Pt. This is what you will have. Correct? The 2 will get cancelled. Clear? I hope all of you got that. Right. So once we get this here, so what is left now? Sorry, minus this is not plus, minus P infinity minus Pt, 2Pt. So now let me write in terms of K. So K is equal to 2.303 by T log of A naught by A naught minus X, which can be written as 2.303 by T log of P infinity upon 2P infinity minus 2Pt. Okay, so simply 2.303 by T log of P infinity by 2 times of P infinity minus Pt. That's it. That is the value of K. Got it? So please go through it quickly, everybody. Check if you have any doubt in this case. Check these questions quickly. What is the time needed to complete two-thirds of the reaction by first order kinetics? Okay, straightforward questions. So let's do it together, everybody. If initial value is A naught, now X is two-thirds of A naught. So which means AT will be equal to A naught minus X. Okay, that is equal to A naught minus two-thirds of A naught, which is one-third of A naught. Hence, T will be equal to 2.303 by K log of A naught upon A naught by 3. Makes it 2.303 by K. K value is 4.77 into 10 raised to minus 2 into log of 3. That this is what you need to get. And solving these values, you're getting this as 23.03 minutes. Because that log 3 value is 0.477 only. So that will get cancelled with here and 10 will come above. Got it? Simple calculation here. In the second question, 3/4 of the first order reaction completes in 32 minutes. What is the time taken to complete 15 by 16 parts of it? Okay. So we use this first case to calculate the K value. So K is equal to 2.303 by time taken, which is 32 log of A naught by 1 by 4 times of A naught. Because if 3 by 4 is completed, 1 by 4 is left. So 2.303 by 32 into log of 4. Right? So that is equal to 2.303 into 2 log 2 by 32. Okay. Now, what is the time taken for 15 by 16 parts? So check out. So time taken will be equal to 2.303 by k log of. Now listen up. If A naught, sorry, if X consumed is 15 by 16 parts of A naught, then AT will be equal to A naught minus X, which is A naught minus 15 by 16 times of A naught or 1 by 16 times of A. So hence, this will be A naught by 1 by 16 times of A naught, which is 2.303 by K log of, can I write this as 4 raised to power of 2, which is 2.303 into 2 divided by K into log 4. So we already learned the 2.303 by K into log 4 value, right? That is coming as 32. So hence T is equal to 32 times of 2, which is 64, in terms of minutes, 64 minutes. Then these are all pretty straightforward questions, everybody. Going to the next one. Calculate T80 percentage given T90 of the reaction is 1 minute. Okay. You have to do the reverse one here. So how much is T80? Based on that, we need to figure out T90. Okay. I'm directly writing the answer here. So T80 percentage will come out to be approximately, uh, approximately how much? Mm, 0.7 times of T90 beta. This is how much you will get. That 80 percentage will be T80 will be equal to 0.7 minutes. Correct. So I hope you guys understood these cases. Yeah. So please go through these regular problems once quickly. Okay. And the next session, we can take more applications of